So now with the understanding of dark matter, we're going to head out to the entire universe. Now in dealing with the entire universe, we have to make some underlying assumptions. These assumptions are encapsulated in what we refer to as the cosmological principle. Okay, so what the cosmological principle assumes is that the universe is homogeneous and that it is isotropic. Okay, so maybe you've heard homogeneous before. Homogeneous means that it has the same consistency or density throughout. Okay, so the place that I'm familiar with homogeneous or homogeneous is milk. Okay, milk has actually been homogenized so that it does not separate the milk and the cream. Okay, where I grew up, we actually had a dairy farm relatively close by, and every once in a while we'd actually get fresh milk from the dairy farm, and it would separate into the cream on top and the milk on bottom. If you wanted to get an even mix, you'd have to stir it up every time. Okay, milk that you buy at the store has actually been homogenized so that the milk and cream don't actually separate, that they stay together and are homogeneous. So we mostly drink homogenized milk. Okay, so homogeneous means that it has the same density or consistency throughout. Now, if we look on the small scale, this is absolutely not true. You do not have the same density as the Earth, or the same density as the Sun, or the same density as space. So we know that this is not true on the small scale. But for the cosmological principle to hold, it only needs to be true on the large scale. So meaning not just the size of galaxies or galaxy clusters, but even larger regions. Okay, so when we get to regions that are about 250 megaparsecs across, okay, so a megaparsec is a million parsecs, okay, these really, really large regions, then this appears to hold true, and that's all we need, is that on this largest scale for it to be correct. Okay, so when we get to the largest scale, we actually do see about the same number of galaxies and voids in any given region of space. Okay, so the other piece to this is that the universe is isotropic. Isotropic means that it is the same in all directions. Okay, there is no preferred direction. Okay, that no matter where we look, everything should be the same in all directions. And again, this appears to be true. Okay, that no matter where we look, we see the same sorts of organization, the same size of objects. But again, this has to be only on the largest scale. But again, this does seem to be true. Now, we can make an extension to the cosmological principle, saying that it's not just the distribution of matter, but that it's actually all physical law that has to be the same. Okay, so that no matter what is happening here on the Earth, the same physical laws must apply everywhere out in the universe. In other words, our position within the universe is not unique. What we see here is what any intelligent being anywhere in the universe must also see. Now, again, this is an assumption, but it seems to hold true. We have done some experiments looking at the most distant galaxies that we can see, and it appears that the physics that we've learned about our own galaxy still apply to those. All right, here's another question. See if you can remember this one from a previous lecture. What is Hubble's law? A, the mass of a galaxy's black hole is proportional to the galaxy's luminosity. B, we see more spiral galaxies in the past than we do today. Or C, the recessional velocity of a galaxy is proportional to its distance from us. Go ahead and think about it, and we'll discuss it in just a second. All right, so the correct answer is C. Hubble's law is the one that relates the distance and the redshift, but the redshift tells us about the velocity, the recessional velocity. So the correct answer is C. Well, if we look at Hubble's law, okay, so we get the general Hubble flow of all galaxies well, I should actually say galaxy clusters moving away from us. Hey, on the small scale, so within our own galaxy cluster, they're not moving away from us. The Milky Way and Andromeda are actually set on a collision course. They are expected to collide anywhere from the next 2.5 billion to about 4 billion years. But when we go to other galaxy clusters, we see that other galaxy clusters are moving away. One way of interpreting that is that we are actually the center of the universe. If you think about an explosion, when stuff explodes, you have all of the pieces moving away from the central point where the explosion happened. So if we trace everything back, then everything has to end up here, therefore we are the center of the universe. How many times have we thought that we were the center of the universe? And how many times have we actually been right? So maybe we should accept that no, we're probably not actually the center of the universe, and therefore something else must be going on. So what we can do is we take both Hubble's law and the cosmological principle. So Hubble's law states that the farther away a galaxy is, the faster it's moving away. And then the cosmological principle gives us the idea that the universe is the same everywhere, meaning what we see here on the Earth has to be true everywhere. So from our point of view, we see all galaxies moving away. What this means is we move to another far distant galaxy cluster. They must also see all the other galaxy clusters moving away. And if we go to some other far distant galaxy cluster, they must also see all galaxy clusters moving away from them. Well, the conclusion is therefore that all galaxy clusters must be moving away from all other galaxy clusters. Well, if that's true, if all galaxy clusters are moving away from all other galaxy clusters, the only thing that could do that is if the entire universe itself was actually expanding. I realize that didn't make a lot of sense, so we're going to use an analogy. So in almost all of the textbooks that I've seen that have dealt with this, they use the analogy of a loaf of raisin bread. Now, personally, I don't know why you take a perfectly good loaf of bread and then ruin it with raisins. So I'm going to propose, instead of raisins, we use chocolate chips. So we have this loaf of cinnamon swirl bread with chocolate chips in, and we set it out to rise. As the loaf rises, the dough itself is expanding. Technically, it's air bubbles within the dough, but the dough itself is growing. As that happens, as the dough is growing, it actually pushes the chocolate chips farther away from each other. And because the entire loaf is growing, all of the chocolate chips are getting pushed away from all of the other chocolate chips. Now, the reason why this is happening is the whole loaf is getting bigger. So, in our analogy, the chocolate chips are like galaxy clusters, and the loaf is like the universe. So the entire loaf of bread is expanding, and all of the chocolate chips are moving apart. Our entire universe is expanding, and all of the galaxy clusters are being drawn apart. So let's go through what some of the consequences of this could be. So we're in this image, we're looking at a snapshot of time. So in the top one, we're looking at a point where we have these galaxies that are 100 megaparsecs apart. So in this instance, from galaxy A to B is 100 megaparsecs, from A to C is 200, and from A to D is 300. Now this is one snapshot in time. Now we will allow the universe to expand. We'll come back later to a time where what used to be 100 megaparsecs has now expanded until it is 150. So at this new time, the distance between A and B is 150 megaparsecs. From A to C will be 300 megaparsecs, and A to D will be 450 megaparsecs. So what this means is that galaxy B moved by 50 megaparsecs, galaxy C moved by 100, and galaxy D moved by 150. So the distance from A to B was 100, it moves to 150, so it had to move 50 megaparsecs. From A to C was 200, now it's 300, it moved 100 megaparsecs. A to D was 300, now it's 450, so it moved 150. Now this motion, how far that distance that it traveled, all happened in the same amount of time. So what this means is that galaxy B, the closest galaxy, moved the slowest, and galaxy D, the one that was the farthest away, moved the fastest. This is Hubble's law. Hubble's law is actually a consequence of a universe that is expanding.